Hi, everybody. Okay, now we're ready to talk about today's main topic, the inverse Laplace transform. And the idea is we consider the following. Suppose that I give you not the original function, but the Laplace transform of the function. Can you go backwards and tell me what was the original function that it came from? So that's what we're going to be looking at today. We will once again be relying on our table of Laplace transforms, so I have a copy of that on the right. And we'll be working through this example number 2, 5 problems here that you can see on the left. I encourage you to try to work through these on your own and come back and double check the answers with me. We'll go through each one step by step. So let's talk about the inverse Laplace transform. This is problem 1. And when we take the inverse Laplace transform, we write L with a little -1 power. That's a sort of common notation for the inverse of some operation. So this is the inverse Laplace transform of 3 over s plus 4 factorial over s to the 5 plus 1 over s minus 7. And we have that s has to be greater than 7. Okay. The first thing that we can do, and sort of the good thing about these, the thing that makes it manageable, is that we have this linearity condition that works in this direction as well. So we can look at the inverse Laplace transform of each of these things. So we have that this is equal to the inverse Laplace of 3 over s plus the inverse Laplace of 4 factorial over s to the 5th. Now, we could, of course, multiply out that 4 factorial, but I think we'll find in looking at the table that the table has a place with the factorial all written in it, and so it will be helpful to us to see it with that factorial written there. So I'm just going to leave it as it is. And then plus the inverse Laplace transform of 1 over s minus 7. Okay, let's take a look at these one at a time. The inverse Laplace transform of 3 over s. And what we're doing is we're looking here at the Laplace transform table for something that looks like the thing that we have here. And then we're going to go backwards and find the function that it came from. Now, 1 over s, that's the Laplace transform of the function 1. We can apply that here, and the reason is that that 3 on the top is a constant, and you can think of that 3 as coming out in the front. So this is 3 times the inverse Laplace transform of 1 over s. So this is 3 times the inverse Laplace of 1 over s plus, and we'll continue that stuff to the right in a moment, but let's just finish with this one first. The inverse Laplace transform of 1 over s is just the constant function 1. So this is 3 times 1, which means that this first part is just going to turn into the number 3. Let's look at the next one. 4 factorial over s to the 5. Well, if we go ahead and look through our table for this one, it looks like the one that has a factorial on the top and s to a power on the bottom is here. And the thing you'll notice is that the n, the number that's in the factorial at the top, is 1 less than the power on the bottom. And since we have 4 factorial on the top and then s is to the power 5, that tells us that n must equal 4. Because 4 factorial on the top and 4 plus 1 is 5 power on the bottom. So let's just make a note of that, and then notice that this turns into 2 to the n. So here we have that a is equal to 4, and the inverse Laplace transform of this is t to the power 4. Now, for the last one, 1 over s minus 7, let's go ahead and see what that looks like in our table. We're looking for something with 1 over s minus a number. And I see that here, 1 over s minus a says that the inverse function is e to the power at. And here, that number a for us is the number 7. So in this problem, I'll just make a note that a is equal to 7 here. And then that inverse Laplace transform is equal to e to the power 7t. Okay. We've now taken the Laplace transform of each of the pieces. This is t to the fourth, and this is e to the 7t. Just simplifying, this is 3 plus t to the fourth plus e to the 7t. That is the function which this came from. And if we were to take the Laplace transform of this function, we would end up back again with this function that is in the middle here. And this same restriction here. Okay, that's the end of problem 1. I suggest, if you have not done so already, pause, work through problem 2. Here are the rest of the problems. I'll zoom in on them. So if you want to pause here and work through problems 2 through 5 if you can, and then come back and check in with me. We'll see how you did. All right, continuing on, let's take a look at problem number 2. 2, it looks like this. It's 1 over s squared plus 25 plus s over s squared plus 25. So the two things that we're taking the inverse Laplace transform of are 1 over s squared plus 25, and then plus s over s squared plus 25. And in this case, s is bigger than 0, so s bigger than 0. Now, when we go ahead and look at our functions, we're looking for, on the bottom, s squared plus a number, and then on the top, one of them has just a number on the top, 1, and one of them has a variable, an s, on the top. So let's go ahead and see what we can find here. Looking down the list here, it seems like s squared plus a squared, this looks pretty good. And the thing that we're missing is a number on the top, that a on the top. Here, you can see from the s squared plus a squared that the a should be 5. And the reason I say that is because our fraction looks like s squared plus 25. And if we would have to put a in equal to 5 in order to get s squared plus 25. So let's make a note of what is the value of a in this. Here we have that a is equal to 5. And the problem here is that we don't have a on the top. We only have 1 on the top. And so here's how we're going to solve this. Let's recopy. This is the inverse Laplace transform of. And the nice thing is that you can do sort of standard algebra. We can do 5 and 1/5. And then s squared plus 25. What have I done? I've taken my fraction, 1 over s squared plus 25. I wanted to put a 5 on the top, so I multiplied the top and bottom by 5. The 5 ends up on the top where I want, and on the bottom, I just put it in the front. I have a 1/5. Now, we'll go ahead and solve this one, but don't forget that we have a whole nother piece to do. We're going to work on this one next. And here again, I am splitting this up into 2 pieces, first looking at this one and then looking at this one, in order to deal with so-called linearity, in order to deal with them separately. Okay, here, the inverse Laplace transform of this thing, well, we have an inverse Laplace of 5 over s squared plus 25. This is exactly the identity. 5 over s squared plus 25 is sine of 5t. And then the only trouble is this 1/5 in the front. The 1/5 can be pulled out in front. And because of that, I'll do this in 2 steps this time, but in the future I won't necessarily. I'll skip this step. This is 1/5, pull it out in front, over 5 over s squared plus 25. And here we still have that a is equal to 5, and this is exactly the Laplace transform of sine 5t. So keeping the 1/5, it's 1/5 sine 5t. All right, that deals with our first fraction. We've taken the inverse Laplace transform of it. Now we look at our second fraction. This is s over s squared plus 25. So we're going to go look back at this table. And the one we were looking at before no longer works for us because on the top we now have an s, and that one has an a constant on the top. But if we look down just one row, s over s squared plus a squared is cosine of at. Now, the bottom is a squared, s squared plus a squared, and that says that a, once again, is 5 here, because that a on the number on the bottom is 25. So a is 5, and you'll notice there's no a on the top, so we don't have to do any adjustment by multiplying the top and bottom by something. We already have an s on the top, and there's no need for anything else up there. So we are once again going to say, for this problem, here we are, problem 2, we're once again going to say in the second part that a is equal to 5. And I think we can just apply that inverse Laplace transform immediately to s over s squared plus 25. And that is equal to cosine 5t. And just copy down to our final answer here. There we go. That is the answer to number 2, 1/5 sine 5t plus cosine 5t. Okay, that takes care of problem 2. Let's take a look at problem 3. Problem 3, 1 over s minus 4 squared plus 9, where s is bigger than or equal to 2. These are getting complicated enough. Well, let's just go ahead and take a copy of that, and we'll put it down below here. This is our problem, and this is problem number 3. So let's consider the inverse Laplace transform of 1 over s minus 4 squared plus 9. And I see, let's see, first of all, there is a restriction, s is greater than 2 here. Second of all, this is a single fraction, and so we can't split it up into different pieces. We really just have to look for something that looks like this. If we're lucky, we'll find something that looks like it. It has a constant on the top. On the bottom, it has s minus a constant, whole thing squared, and it has another plus another number. So let's go ahead and see what that looks like here. Looking down, here it looks like there are some that have that s minus a number, s plus a number on the bottom, whole thing squared plus another number squared. This one has just a number, a constant on the top. This one has s minus a constant on the top. None of the other ones look exactly right. This one doesn't have that plus b squared on the outside and so on. So what I'm going to do is we're going to focus on using this one. And we're going to try to determine what is the A and what is the B, right? And we'll come back over and we'll look at that in more detail if we need to. This is 1 over s minus 4 squared, and the formula says it's b over s minus a whole thing squared. And that means that that a must be equal, in this case, to 4. So this, because of the s minus 4 that is squared, we get that a is equal to 4. And then, similarly, the number that comes afterwards, the plus b squared, here, well, we have plus 9. And what does that tell us that b must be? B must be 3. It's plus 3 squared. That's the same as plus 9. So here, once again, here is our problem, and b is equal to 3. Now, the only trouble is that in this formula, we also have on the top of the fraction, we have that number b itself. And in our problem, we only have the number 1 up here. This will be a problem if we want to apply this template, this formula. And the thing that we need to do that we can manipulate easily is the number on the top. In order to get the number b that we want on the top, we can multiply the top and bottom by b. In this case, that number b we just established was equal to 3. And so what I'm going to do is I'm going to first rewrite this by putting, let's see, we have our s minus 4 whole thing squared plus, I'll rewrite it as 3 squared just so it fits the template very nicely. I'll put a 3 on the top, but if I put a 3 on the top, I have to divide by a 3 outside. This is sort of one way of looking at putting a 3 on the top and on the bottom. And since this one is a constant, I can move it out into the front. And now this looks exactly like the template. The answer for this inverse Laplace transform is, if we look carefully at this one here, this is e to the at, so that's going to be e to the 4t, sine bt, or sine 3t. So this one is, I keep the 1/3 in front, that's e to the 4t times sine of 3t. And that is our inverse Laplace transform for number 3. Let's take a look at number 4. So once again, we'll do a quick copy. Number 4 here This is the inverse Laplace transform of 1 over s minus 6 whole thing to the power 7 plus 5 over 2s minus 7, where s is bigger than 6. Okay, so let's go ahead and work our way through this. This is the inverse Laplace transform, and I'm just going to go ahead and split this up already. 1 over s minus 6 to the 7 power plus inverse Laplace of 5 over 2s minus 7. And the whole thing has this restriction s greater than 6. Let's take these one at a time. This looks like 1 over s minus a number, whole thing raised to a power. So there should be an s minus a number, and the whole thing raised to a power. We go and look at our table for this. Let me see. If I go down to nearly the bottom, I have a number on top, n factorial. We can sort that out later. But on the bottom, I have s minus a power. I'm sorry, s minus a number, and then to the power down there. We have two constants running around, s minus a. So a is that constant that follows the negative sign on the bottom. In our case, a is equal to 6. So here we have a equals 6. And the other one is n. The power here is n plus 1. So if this is n plus 1, or the 7, then n must equal also 6. Why 6? Because if you add 1 to that n, you should get the power on the bottom. Okay. What are we missing? We're missing the n factorial, or 6 factorial, on the top. But luckily, 6 factorial is itself a constant, so we can go ahead and put that in there as follows. Let's do this in this way. Let's see. I'm going to put s minus 6 to the power 7. I would like to put 6 factorial on top, so I'll put 1 over 6 factorial in the front, and those are connected by multiplication. Now, I am not going to write the extra step of moving this 1 over 6 factorial out to the outside. I'm just going to do that in my next step. I'm going to keep that there, and then I'm going to take the inverse Laplace of this thing. And of course, don't forget, we have a second term to deal with. We're going to come back and work on that. All right. So this is 1 over 6 factorial. Don't forget the factorial. And then this part, this is our n factorial over s minus a to the power n plus 1. And as we see from our table, that one, if we know a and we know n, which we do, this is t to the n, e to the at. Let's go ahead and plug it in. So this is t to the power n was 6, and then e to the power at, so e to the power 6t. So this came from the Laplace, inverse Laplace transform, and the 1 over 6 factorial is just left over from the constant we pulled out to the front. That's halfway through this problem. Now we come to the second half, which is the inverse Laplace transform of 5 over 2s minus 7. Let's go ahead and take a look. What do we have? What do I notice? A number on the top. We're going to be able to manipulate that by multiplying the top and bottom by whatever we want. On the bottom, however, we have this 2 in front of the s. That's a little bit annoying. We'll have to deal with that maybe. But if we ignore the 2 for now, it's like an s and then minus a constant. Okay, we'll have to deal with the 2, but it's the s minus a constant is the main thing there. So let's take a look. Do we have a number over s minus a constant? And it looks like we do have such a thing. It is located right here. It's got to be 1 over s minus a. So a couple things to notice. We need a 1 on top. The other thing to notice is that on the bottom, we have 2s minus something, whereas the formula only has s minus something, which means we cannot apply this immediately. And we're going to deal with that right now. Here's how we do it. We're going to do it, handle all of these problems through the idea that that constants multiplied or divided by our function can be pulled outside of that inverse Laplace transform. So let's go inverse Laplace and then just give ourselves a little room inside. First, I want to do this. The 5 that's currently on the top, I'm just going to move it over here and make it a 1 on the top. If these two fractions are multiplied together, 5 times 1 gives us 5 on top. So that has not changed anything. The other thing I want to do is factor a 2 out of the bottom. Now that might seem impossible because 2 does not go into -7 evenly, but it does go into -7. -7 divided by 2 is -3.5. So this is s minus 3.5. So looking at this picture now, first of all, you can double check that the bottom is still the same. It's 2 times s, and 2 times minus 3.5 does give you 2s minus 7. The other nice thing is that this constant is now multiplied by the entire bottom, which means that we can move it out to the fraction that's being multiplied in front. So what does this look like? This is like the fraction 5 over 2 times the fraction 1 over s minus 3.5. And this one, 1 over s minus 3.5, that one we know. That shows us that our a is equal to 3.5. And 1 over s minus a, if we just rewind, 1 over s minus a is e to the power at. And here our a is 3.5. So let's go ahead and take that inverse Laplace transform. We do, of course, have that fraction in the front, that one right there. And the nice thing is that that fraction is entirely made of constants, so it can just come out into the front. So this is 5 halves. And then we said that 1 over s minus a, the inverse Laplace of that, is e to the s, that's 3.5 times t. Okay. Simplifying our first term, I will just leave this as 1 over 6 factorial times t to the 6 e to the 6 t. So this is our inverse Laplace transform of 1 over s minus 6, whole thing to the 7 power, plus 5 over 2s minus 7. And as you can sort of see, looking at the table and looking at these functions, sometimes the functions just match what's in the table perfectly, and sometimes you have to do a little bit of algebra work to rewrite them so that they match what's in the table. That was the strategy that we used in the second one, factoring out the 2 on the bottom and moving that 5 off of the top. Okay. Let's take a look at number 5. So, number 5, here the function is 5 over s squared minus 8s plus 41. So let's go ahead and try the inverse Laplace transform of this. 5 over s squared minus 8s plus 41. Now, things to notice. First, it's a single fraction, so we can't right now split it up into pieces. We have to look for the whole thing. On the top, we have a constant. That looks good because whenever we have a constant on the top, we can change the value of that constant on the top just by multiplying the top and bottom by something. In addition, on the bottom, we have s squared. Oops, that was a mistake. We have s squared. And then we have minus 8 times s. That's a little odd. I haven't seen something on the bottom with just a plain s as well as an s squared in it. But maybe there's something in our table that fits. And then plus 41. So it looks like on the top a constant, and on the bottom it's a quadratic. You know, as squared plus bs plus c, something like that. Let's go ahead and take a look at this here over in the table. So on the top we're looking for a constant. On the bottom, we're looking for a quadratic. Now, looking through these, this has a constant on the top, a on the top, and on the bottom it has an s squared and then a constant squared, but it doesn't have a plain s term in it. So this is tempting, but not exactly right. This has an s on the top. We don't want to do that. This has an s on the top. This has an s on the top. We only have a constant on the top, and although we can change that constant, we can't introduce an s up there without causing trouble elsewhere. This looks hopeful. It has an s, it has a constant on the top, But here it's an s minus a squared and plus b squared. It doesn't just have an s squared plus an s plus something with a constant. So this is maybe similar, but not exactly right. This one has an s on the top. This one has a constant on the top, and on the bottom, it looks like s minus something to a power, but it doesn't have s squared plus that s term plus a constant. So I would say this is maybe hopeful. We might do something where we multiply out the bottom with that power there. Or this one, let me see, where did it go? This one looked hopeful, but once again, this doesn't have that s term in it. And so it's not entirely clear how we would do this. So I'm going to put right here that it doesn't seem to match anything in our table. The closest match is the e, I believe it was e to the at sine bt. Let's just double check that. Yeah, here it's e to the at sine bt, and that looks like b over s minus a squared plus b squared. So this looks like, if we look at the Laplace transform of that, it looks like b over s minus a squared plus b squared. Question. Can we rewrite our fraction to look like this? So we are not actually going to solve this problem now. We're just going to wrap up and say this is one that we're stuck on. But can we rewrite our fraction, and by our fraction I mean this thing, in this form? And by this form, I mean the right-hand side of this equation. So we will address this next time. We will try this next time. This is one of those cases where we might be able to rewrite this, but that rewriting is going to take a little bit more algebra, and we're going to talk through the strategies for it. This would be our best bet of how to rewrite it. All right, that's it. Feel free to ask your professor if you have any questions, and give the associated web work assignment a try. See how you do. Bye-bye.